Can start now. So, well, it's here, but let me read it. Maximal dissipative operators on metric graphs, real eigenvalues and their multiplicities, talk by Pavel Kurasov, University of Stockholm. So, please.
Okay. Thank you very much for the invitation to speak at this conference. I think it's... So, do you hear me?
Yes, very well. At least I hear
Okay,
you.
good. Okay, there was some comment. So thank you very much for the invitation, and I'm very happy to meet old friends. And I think that this is a great idea to have such conferences.
Thank you.
No, I mean that one organizes conference in different. There are different scenarios how you organize the conference. Either you have focused during a few days, you have hundreds of talks, or you spread them over the extended period. So let us see what is the best option. Yes. Okay. So and this is a joint work with Sergei Nabokov, who unfortunately passed away already 3 years ago, and my PhD student Jakob Müller. And also, I wanted to dedicate this talk to the memory of some time ago. Oh, so today I will speak about before slides, if it's possible.
So there seems to be a problem with your connections. We don't listen to you well.
Yes.
So can you hear me?
Now, yes, but before was we could not.
I'm sorry. Can you hear me now?
Yes, now I
Can I
hear
continue?
you. Yes, please continue.
Okay. Okay. So today we'll speak about dissipative operators. And by dissipative operator, I mean densely defined operators such that the quadratic form of the operator has a non-negative imaginary part. So it means that the semigroup e to the power ILX is contracting. Sometimes people use the semigroup e to the power minus LT as contracting, but here I have this I. So it means that, so to say, these operators, they have a spectrum in the upper half plane. And I will speak about such operators on metric graphs. And preparing the talk, I hope that I will not be the first to speak about metric graphs. But nevertheless, I am the first, and I think for the understanding of the talk, I will need to repeat a little bit, because many of you know what is a metric graph, but I will give a slightly updated definition of it. So what is a metric graph for me? Usually in discrete mathematics, when you define the graph, you start with the vertices, and then you consider edges as just connections between the vertices. But defining metric graphs, you start not from the vertices, you start from edges, which are just finite intervals. So we take several compact intervals of the real line. They belong to different copies of the real line. So there should be no 2 points with the same coordinate on these intervals. And then you put together all the endpoints of these intervals. So if you have n intervals, then you have 2n endpoints. And then you identify some of these endpoints. So it means that you divide this set of endpoints into equivalent classes. Equivalence classes, these are vertices. So you build vertices as some kind of secondary objects. For example, here I have a graph where there are 1, 2, 3, 4, 5, 6, 7, 8, I think 9 edges. And then you have vertices. For example, this vertex consists of 3 endpoints. This vertex consists of 4 endpoints. And they are considered supposed to be equivalent. So it means as a geometric object, metric graph is simply a union of these intervals factorized by this equivalence relation. Okay, so today we are going to speak about a class of Schrödinger operators. And of course, since I will speak about dissipative operators, I will not assume that the potential is real. So it means that I have a second derivative plus q, which is a potential, times psi, and q is not real. It can be real, but it's not assumed to be real. But then in order to make this operator reasonable, as in the case of self-adjoint operators, we need to assume some vertex conditions. Starting from the old paper by Kastrik and Schrader for these operators on metric graphs, these conditions can be written in the form. So you take a vector, this vector psi, this is the vector of all limiting values of the functions at the vertices. So it means at the endpoints of the intervals. So you see that you don't assume that the functions are continuous on this graph. But this, you assume just that they are continuous on the edges because they should supposed to be from the Sobolev space W22, so they're continuous, and their limiting values at the endpoints are well defined. You make a vector. Then you do the same with the derivatives. Here there is one special thing that you need to take derivatives which are oriented because you consider this object as a geometric object. So in principle, you don't know in which direction you parameterize each of the edges. Therefore, you take the derivatives which are pointed inside the intervals, inside the edges. And then having these intervals, you pick up two matrices, A and B, such that this relation holds, this relation which is here. So usually there is a plus here, but today it will be easier to have minus. This is the main difference to the canonical A-B vertex conditions introduced by Kastrykin and Schrader. And of course, you need to introduce sufficiently many conditions. So it means that these matrices should have the second dimension 2n, which is small d, but we don't know how many conditions we introduce. We can introduce 1, 2, 3, 2n conditions, and so on. Okay, so the first is to find necessary and sufficient conditions for such Schrödinger operator to be dissipative. And the first lemma, which is really easy, it states that this operator of this type is dissipative if and only if two separate conditions are satisfied separately. That first, the imaginary part of Q is non-negative. And then for any psi and d psi that satisfy the above mentioned conditions with the matrices A and B, the imaginary part of this, so to say, quadratic form is also non-negative. How do you prove this lemma? So you simply look at the quadratic form of the operator. And the quadratic form of the operator by integrating by parts is given by this formula. First, you have the integral of the first derivative squared plus q times the psi squared plus the contribution from the vertices, which is exactly this quadratic form which is standing here. Yes. Then if you take imaginary part, then the first term in the integral is real. So it means that you just get imaginary part of q times psi squared plus imaginary part coming from the limiting values at the vertices. And then you remember that the values of the vertices cannot be, so that you have a function that L2 norm of the function cannot be used to estimate the values of the function and derivative at points. So it means that these two integrals have to be non-negative separately. And of course, the first integral is non-negative if and only if imaginary part of Q is positive, it is non-negative. And the second is non-negative only if and only if this inequality is satisfied. So it's easy. But for our Schrödinger operator from our class, given by this second derivative plus potential, and these AB conditions at the vertices, we prove that it is maximally dissipative if and only if. Again, Q is not positive. The rank of this matrix A is equal to N, as in this, which is self-adjointness, yes? And then the second condition that may non-negative. This is the reason why I said A because doesn't have here which is strange. Yes. For self-adjoint, you have imaginary part of Q, and this condition is P is self-adjoints, or in a way that imaginary part.
Se desconectó él. Ah. Well, I guess Pavel got disconnected. Oh, he's back. ¿Tiene sonido? Can you hear us? Sí, pero tiene sonido. We don't see your screen, Pavel, and we don't listen to you. Un mensaje, ¿cómo? ¿Dónde está? Sí. No.
Ricardo, perhaps you can send him an email.
This is what I am doing. We do not hear you.
Can you hear me now? Sorry.
Yes, now we hear you.
Because you see, for some reasons, my microphone was, when this stopped, that my microphone was switched off. So
Okay, you need to share your screen now.
yes. So
That's
can you
fine. That's okay.
when I disappeared, at which point?
Well, you were discussing theorem 4.
Okay, theorem 4. Okay, so I can repeat a little bit. Okay, so the theorem 4 states that not only that this the operator is maximal dissipative, not only that Q is positive imaginary part, the rank AB is equal to N. This is the same condition as in the self-adjoint case. And the imaginary part of AB star is greater or equal to 0. In the self-adjoint case, you have condition that Q is real, the rank AB is n, and AB star is Hermitian, which means that imaginary part of AB star is simply equal to 0. Yes. So, but important thing that this theorem not only states that this operator is dissipative under these conditions, but it is maximal dissipative, which means that there is no other dissipative operator which is an extension of this one. So for this reason, you have this condition that the rank of AB is equal to n. This is somehow reflects that this is maximal dissipative operator. And a good example of maximal dissipative operator, this is an operator with so-called delta couplings. So it means that in the future, in the rest of this talk, I will restrict the presentation to delta couplings, which means that the function is continuous at every vertex. I already told you that the function have to be continuous on the edges, but now they are also continuous at the vertices. And then at every vertex, the sum of oriented derivatives, first derivatives, should be equal to the value of the function at the vertex. It is well defined since the function is continuous, times the parameter alpha m. And then this condition of dissipativity means that the imaginary part of alpha m is non-negative. Okay, so this is just general theory of completely non-self-adjoint operators, that the operator is L is called completely non-self-adjoint if and only if there is no reducing subspace V such that the restriction of L to V is self-adjoint. And here the main theorem concerns so-called Langer decomposition. Suppose that this real spectrum of the operator A consists only of the eigenvalues. Then the operator A possesses Langer decomposition. So you take HS, this is a span of all eigenfunctions corresponding to real eigenvalues. And of course, restriction of A to HS is a self-adjoint operator. And then the rest of A, which is a direct sum, orthogonal sum, so it is completely non-self-adjoint. So, and our goal is to study these Schrödinger operators and understand under which conditions, additional conditions, these operators don't have real eigenvalues, or they have real eigenvalues, but then estimate their multiplicities. Okay, so first of all, on the first step, we introduce a notion of a dissipative H. Suppose that psi is an eigenfunction corresponding to a certain real eigenvalue lambda. Yes? Then if I just take the quadratic form of this. Oh, sorry, here there is a misprint. So U is equal to psi. Yes, even psi is the same thing. So then lambda psi square will be equal to psi prime square plus integral of Q times psi square plus contribution from the vertices. Yes. And if I take imaginary part, remember that we take lambda real. So it means that on the left-hand side, I have something which is real. Then the right-hand side should also be real. So which means that integral of the imaginary part of Q times U square plus of psi square plus contribution from the vertices should be equal to 0. But this contribution from the vertices is non-negative. Yes. So it means that in order to this to be 0, I need that integral of imaginary part of Q times psi square must be equal to 0. Yes. So it means that if I have an edge where imaginary part of Q is not 0, then psi has to be identically equal to 0 on this edge. Yes. Therefore, we introduce notion of dissipative edge. This is an edge such that there is a certain set of Lebesgue measure strictly greater than 0, where imaginary part of Q is not 0. Yes, this is a dissipative edge. And the statement is the following, that if edge is dissipative, then the self-adjoint part of the operator L coincide with the self-adjoint of the operator with the self-adjoint part of the operator L restricted to the graph gamma when where I take away this dissipative edge. Yes, so this is a simply restriction of the operator on all the functions which are identically equal to 0 on this edge. Okay. So then we also have dissipative vertices. Because if I do the same thing as before, remember that U is equal to psi. I'm extremely sorry for this misprint. Yes. So then this should be equal to 0. But the first term is non-negative. So it means that for this sum to be equal to 0, the second term should also be equal to 0. But in the case of delta conditions, the second term is simply equal to the sum over vertices, imaginary part of the coupling constants AM times the values of psi at the vertices squared. And this is equal to 0 only if imaginary part of alpha M are equal to 0, or the values of psi at these vertices equal to 0. So it means that at dissipative vertices where imaginary part of alpha M is positive, strictly positive, the function psi has to be equal to 0. Yes. So, but what does it mean that the function psi is equal to 0 as a certain vertex? Yes. So you see, psi should satisfy these delta conditions. So it means that the psi should be continuous. If it is equal to 0, then it means that psi is equal to 0. But then also the sum of derivatives must be equal to alpha M times the value of the function at the vertex. But if the value of the function at the vertex is 0, it means that the sum of the derivatives should be 0. So it means that this function should satisfy both Dirichlet and Kirchhoff condition. The second is a so-called Kirchhoff condition, that the sum of derivatives is equal to 0. This is like Kirchhoff's law that the sum of currents through every vertex in an electrical network must be equal to 0. Therefore, we have to introduce so-called Dirichlet-Kirchhoff vertices. Yes. So these are vertices where the function should satisfy both Dirichlet and Kirchhoff condition. Okay. So the first reduction. So we are looking for real eigenvalues of a dissipative Schrödinger operator on the graph. So, and the first thing that we have to do, we have to remove dissipative edges, because on dissipative edges, psi must be equal to 0. The second step, we should also, instead of, if we have these dissipative vertices, there we have to introduce Dirichlet-Kirchhoff conditions. Yes. So I was hoping that somebody can answer the following question. Can Dirichlet-Kirchhoff conditions appear at some other vertices? No? Okay, so nobody wants to answer the question. So you see, if we go back here I was not on purpose, but I didn't show the last two lines of my slide. Yes. Suppose I have this dissipative edge. The function on this dissipative edge must be equal to 0. Yes. So it means that the function, if we assume this delta condition, that the function must be equal to 0 at the vertices to which this dissipative edge is attached. Yes. And then using the same reasoning as for dissipative vertices, we see that the function satisfies Dirichlet and Kirchhoff conditions at the vertices where dissipative edges are attached. Yes. So it means that these Dirichlet-Kirchhoff conditions appear at dissipative vertices and also at the vertices where dissipative edges are attached. But on the left, I have a graph. Yes. This is on this graph, all usual vertices with real coupling constant are marked by circles. And by bold points, the dissipative vertices are marked. Then by dotted lines, we mark dissipative edges. So let me just start here. So for example, here, this edge, you can see it is dissipative. So it has to be removed from the graph. Then here I have a degree 1 dissipative vertex. If I have a degree 1 dissipative vertex, then the corresponding in the neighboring edge, I have to assume that the function is 0, yes, at this endpoint, and also the first derivative is 0. It comes from the delta condition. So it means that the function must be equal to 0 here. So this edge is redundant. Yes. But then I have a degree 3 vertex. Here I have dissipative edge, redundant edge. So it means the function must be equal to 0 also here. This edge is also redundant. But now I come to a degree 3 vertex where only one edge is redundant. Yes. So I cannot continue. Okay, let us look at this. Yeah, as a result of this, here on the new graph, where I removed all these vertices, all these edges, I will get Dirichlet-Kirchhoff condition at this point. So this vertex becomes Dirichlet-Kirchhoff vertex. Yes. Now I have simply a dissipative edge which connects two vertices. So I have to remove this edge, and then I will get Dirichlet, sorry. And then I will get Dirichlet-Kirchhoff conditions at the points where it was attached. So here I have a dissipative vertex. So it means that this edge is redundant. I'm getting here Dirichlet-Kirchhoff vertex for two reasons. Redundant edge is attached, and the edge and the vertex was dissipative, and so on. So you see, I'm getting a graph which is smaller, and this graph is called Hermitian core of my original graph. Yes, and now I can see that it has the following structure. So there are certain metric graphs like here and this one, and they're connected via Dirichlet-Kirchhoff vertices. So here there is another metric graph. Yes. Here there is another. So it means that what is good is it will be good to use the language of hyper edges, because one can consider these graphs, metric graphs, as hyper edges. So this is a metric graph which has 3 contact points. In the original graph, every edge had only 2 endpoints. Yes. Now it will have 3 or maybe 4 or maybe 5. Okay. So therefore, in order to proceed, we will consider three Schrödinger operators on this Hermitian core. We only have to analyze this Hermitian core, nothing more. So all these operators are given by Hermitian Schrödinger operator with real potential, because potential is real on this Hermitian core. If I have some inner vertices, at these vertices I have delta conditions with real coupling constants. I also keep them. So everything is Hermitian. But I consider three different operators. The first operator is when I put Dirichlet conditions at these special Dirichlet-Kirchhoff vertices, but not Kirchhoff condition. So that means that this operator becomes self-adjoint. Another operator is when at these Dirichlet-Kirchhoff vertices, I assume only continuity and Kirchhoff condition. This is so-called standard conditions. I will get another standard, another self-adjoint operator on the same metric graph. And then the third operator, this is a common part of these two operators. This is operator which is determined by Dirichlet and Kirchhoff conditions in these special points, and some self-adjoint delta conditions at all other vertices. So it means that this LDK, the third operator, this is symmetric operator, which is a common restriction of Dirichlet operator and standard operators, which are self-adjoint. Yes. And then the question whether this LDK has eigenfunctions corresponding to the real eigenvalues is extremely simple. It means that we have to understand whether these two operators, Dirichlet and standard operator, have common eigenfunctions. It's not enough that they should have common eigenvalues. They should have common eigenfunctions. If they have common eigenfunctions, that the operator on the original metric graph is not completely non-self-adjoint. So, for example, here we return back to the same condition. Yes. So the Dirichlet operator is defined by Dirichlet conditions at all black vertices. So it means that it falls apart into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 metric graphs. They are not connected. The standard operator, you introduce standard conditions at these vertices, and then this graph is connected. Mm-hmm. Okay, so how to introduce the language of hypergraphs? So we look at the same graph as before, and then each of these metric graphs, which is a part which we get by putting these Dirichlet conditions, forms a hyper edge. So this hyper edge can have one contact point like here. Yes, it may have two contact points and may have three. So here on this picture to the left, these hyper edges are shadowed by very light gray color. Yes. And then some of the contact points of these hyper edges are connected into hypervertices. And of course, hypervertices may have 1 point, 2, 3, and any integer set of points. So it means that in order to introduce a hypergraph, we simply take a certain set of contact points, and we divide it into two different equivalence classes. One is called hyperedges. The other one is called hypervertices. But what is important, that behind every hyperedge, there is a metric graph. Okay, so what is a hypercycle? So for usual graphs, metric graphs, the cycle is simply a sequence of edges, so that one of the endpoint of the one is the endpoint of one edge is the starting point of the other edge, and they form a circle. The same definition is valid for hypergraphs, but the only thing that now they are hyper edges, which means that, for example, here you have a hypercycle, yes, but for example, these two hyper edges, they have two common points. And when you introduce a hypercycle, you distinguish whether these two edges are connected along the left common point or along the right one, which means that hypercycle is not always a subgraph, because as usual, sub-hypergraph is a subset of the bigger graph, yes, which preserves all connections. For example, if there would be only one common point between these two hyper edges and these two, then this hypercycle would be a sub-hypergraph. But if there are two connections or more, then it's not a sub-hypergraph. So, and of course, one can introduce hypertrees. These are hypergraphs without cycles. And for these hypertrees, you can prove the following elementary formula. So here you take a sum over all vertices which have a degree which is greater or equal than 2. Or if it is 2, then the contribution is 0. So it means that this sum should be greater than equal than 3, actually, yes? So because these hypertrees can branch at the vertices as usual trees. But the second sum is the sum over hyper edges, because hypertrees, they can also branch at the hyper edges. And here there is a similar sum, which is in the case of usual graphs is equal to 0, because there every edge has only 2 contact points. Yes, and then it will be equal to t, which is the number of terminals. For example, in this example, we have 1, 2, 3, 4 terminals. Oh, so sorry, 1, 2, 3, 4, 5, 6 terminals. Yes, these are the graphs which are connected to the rest only by 1 contact point. Yes, and minus 2 times the number of connected components. For example, for this graph, the number of connected, the graph is connected, the number of connected components is 1. So the right-hand side is equal to 6 minus 2 is 4. Yes. On the left, I should have the first sum is over all vertices, which have degree greater or equal than 3. And how many such vertices are? Is 1, 2, and 3. They have degree 3. 3 minus 2 is 1. So it means that it will give us 3. And then we need to take the sum over all hyper edges. Again, over all hyper edges having more or equal than 3 contact points. So there is only one such hyper edge. It is this one. So it means it will be 1. So 3 plus 1 is equal to 6 minus 2. This is this formula, because these terminals, they appear when the hyper tree is branching. And the hyper tree can branch at vertices and at the edges also. So for usual graphs, this formula contains only the first sum, and the second sum is 0. So in particular, from this formula, you can prove that twice the number
is equal
of
to
connected
6
components
minus
2 is 4, is less or equal to the number of terminals. And one can prove when the lower bounds are attained. But this is not so important. Then, if we look at the eigenfunctions, it appears that the eigenfunction can be treated rather easily on
We don't listen to you, Pavel. I guess you got disconnected from. Sí tienes sonido, ¿no? Your audio seems to be disconnected. Because we see you, but we do not listen to you. Oh, now. A ver, dale sonido a todos, ¿no? Sí. Porque parece que a todos se nos está hablando. ¿Tienen todos sonido?
So, I'm sorry.
We listen to you again, yeah.
So, when did they disappear? I didn't. When I
Well,
started to speak
I
about the
guess-
hyperclusters, yes?
Yes, I think so.
Okay. You see, these hyperclusters, these are formed by cycles which are not independent. For example, here in this graph, there is this dark gray hypercluster. Then there is another hypercluster which is simply a cycle, yes? And then there are simply these, so to say, pendant edges which are also can be considered separate. Okay, so how this factorization is done? So if we have this graph, this is a part of our graph, yes, and we introduce Dirichlet conditions here. When Dirichlet conditions are introduced, then formally these vertices are split into two if we keep this part of the graph, yes, this connected component. But then we have to reintroduce the connections which were present in the original graph. So it means that in this case, we will have a hyper edge with just 3 contact points. Okay, so then we have a second reduction. We had the first reduction where we removed edges where the potential has a positive imaginary part. Now we have to make a second reduction, because first of all, we should remove all hyper edges which don't have lambda as an eigenvalue. Yes, so a lambda should be an eigenvalue of the Dirichlet operator. Otherwise, the function is 0 on this hyper edge, and it should be removed. So they are called redundant. And then you do the same thing as before. You make the same procedure, removing all these redundant factors, and you end up with something which we call Hermitian hypercore instead of Hermitian core, because now our graph consists of hyper edges, and we again reduce our analysis to this hypercore. So now it looks like I have to speed up, but I don't know how to explain this. So you see, if you have a hyper tree, yes, then the question whether the operator is not completely non-self-adjoint is rather trivial, because you should have lambda should be an eigenvalue on every hyper hyper edge, yes? And then if you have an subtree of these three, or you have a path from one point, one terminating point to another one, then on this path you can always produce an eigenfunction. Yes. So it means that the multiplicity is simply counted by the number of such passes. Yes. So in general, for general hypertrees, you can calculate this dimension, the number of passes. So this is connected with the following objects. First of all, this is the number of connected components and the multiplicity of this eigenvalue on every edge, hyper edge. And valencies. Valency, this is of a hyper edge. This is the number of connections to the other, to the rest of the graph. Yes. So, and finally, we can, so if for hyper trees, this is an inequality, we can calculate the multiplicity of the corresponding eigenvalue. Then for general graphs, we'll get only an estimate. Because for general graphs, the same formula as before gives an upper estimate for the multiplicity, because this multiplicity could be small. So let me just finish with giving an example, showing how complicated this problem is. For example, if you have a cycle formed by two edges, and at the vertices that connect these two edges, we have both Dirichlet and Kirchhoff condition. Yes. Then whether there is a real eigenvalue or not depends on the lengths of these edges, because if the lengths of these two edges are rationally dependent, then you have an eigenfunction on this circle which is equal to 0 at both points. Yes. For example, if you have a so-called watermelon graph formed by several parallel edges, yes, then you get such an eigenfunction only if two of the edge lengths are rationally dependent. Yes, and of course, the multiplicity depends on how many rationally dependent pairs you can find here. So what we were fighting for? For example, if you have such a graph, which is presented here, and you have these black bullets, which determine where we have these Dirichlet and Kirchhoff conditions. Then if we use our general estimate, then what happens there? B1, this is the number of cycles in the hypergraph. This hypergraph is formed by two hyper edges. One is simply interval of length L1, and the other one is the lower graph, which is some kind of circle with two attached intervals. Yes. So then the hypergraph, the number of cycles in the hypergraph is just simply equal to 1. So it would be with twice times 1 minus the number of connected components is 1. And suppose that all the eigenfunctions, all these lengths have, all these edges have the same length 1. Then this sum will be equal to 1. And we're getting 2, which is the correct multiplicity of this eigenvalue mentioned here. So on the other hand, if you don't use this language of hypergraphs and you try to estimate the multiplicity of this eigenvalue using just usual graphs, then the key point is that this graph will have 2 independent cycles. So it means we have 2 here. So it means that it will be 2 times 2, 4 minus 1, and this sum will be equal to 0. We are getting 3. which is wrong. It is upper estimate, but not as good as the estimate that we get using the language of hypergraphs. Okay, so what is the conclusion of this talk? So is that in order to answer the question whether the Schrödinger operator with complex potential is completely non-self-adjoint on the graph, so you have to use the language of hypergraphs that we try to characterize. Yes, and only the language of hypergraphs gives correct estimates of the multiplicity of these eigenvalues. What is interesting that these estimates on the multiplicity of the eigenvalues, they can be used even for usual graphs, and they are sharp in the sense that I can find graphs where these estimates give correct multiplicities. And I don't know, I was trying to speak about non-self-adjoint operators on graphs, and I think that this is the future of this theory, but let me just make a small promotion of somehow, if you're interested about self-adjoint operators on metric graphs, then so you please read my recent book where a lot of spectral properties and a lot of connections between the spectral theory of operators on graphs and general Fourier analysis are established. So thank you for your attention. And sorry for these disturbances. Yeah.
Well, it was okay. It was okay. So are there any questions? Oh, Jan has a question.
Yes. Could you go back to, I think, proposition 6, close to the beginning?
Oh, definition. Now I have proposition 1.
Okay, maybe 1. Yeah. So proposition 1, yes.
Okay.
So do I understand correctly that you assume that A is a dissipative operator?
Yes.
Oh, okay. I mean, this is not written. So
it's not written, but somehow I thought that I speak only about dissipative operators.
Okay. But not necessarily maximal dissipative.
Wait 1 second. No, it should be maximal dissipative.
Maximal.
Yes.
So this is who proved this theorem? Is it?
Okay. Okay. So it's recent Sekefalvi-Nods, I think, who proved it simultaneously as Langer. So somehow there is a difference between several months.
When?
So if you press me, then I will answer 65, 66.
Okay.
But I'm not sure about this date. I can send you the date, the correct.
I mean, just curious. Thank you.
Any other question? Well, I was wondering if you have some ideas on results. Say, once we know it's maximal non-self-adjoint, questions like some scattering for these operators, or if you have thought about those.
Scattering.
Well, this you mainly talk about compact.
Yes, because then the corresponding scattering operator will be contraction, I think.
Yes.
Yeah, so it's but this we have not studied, but I think it could be studied.
Okay, well, thank you. So any further question? Well, otherwise, when we thank the speaker. And then, well, we will meet tomorrow at 9, always Mexico City time. Let me remind you that the talks are recorded in both the YouTube and the Facebook channels of EMAS. And in the emails with the, well, login, you find the login there for the channels too. So if you wish to listen to them again. Okay, so if wonder if there is any other comment or something you would like to say something. Well, okay, so I guess if not, then we can finish the session for today, and we meet you tomorrow, right? Okay.
Yes, thank you. Thank you. Bye-bye.